In this video, we will be learning about how to communicate structures of organic molecules. We will be looking at a lot of pictures this semester of different molecules and different substances. A lot of times we will show either in the textbook readings or in the lecture slides three-dimensional representations of the molecules. But on your exams and homework and whatnot, you will often be drawing two-dimensional structures. And so we have this wedge dash structure, which is the kind of in-between of a three-dimensional drawing and a two-dimensional flat drawing to try to emphasize what is the three-dimensional aspects of it. All of these are representations of the same organic molecule. All of these are cyclohexane. And so you can see all the different representations of cyclohexane. We have to remember that even if we draw a molecule flat with right angles between bonds, that's not really how the molecule is shaped. In Chem 3A, they cover VSEPR theory. If you do not remember that, you can flip to an earlier chapter of your textbook to review VSEPR theory. VSEPR theory says that the electron groups around a central atom are going to try to get as far apart from each other as possible. And so a carbon, which has 4 covalent bonds, those 4 covalent bonds are going to spread out until they're 109.5 degrees apart. Water and alcohols are going to have the same electron group geometry, tetrahedral, but 2 of the corners are occupied by lone pairs of electrons. And so the overall molecular geometry is bent. Nitrogen also has a tetrahedral electron group geometry, so it has 4 things around it. However, only one corner of the tetrahedral is occupied by lone pairs, and so this gives a tetrahedral pyramidal geometry. If carbon has 1, 2, 3 electron groups, it instead is trigonal planar, which has bond angles of 120 degrees. And carbon can also form triple bonds with itself, and this would give it only 2 electron groups, so that the bond angle is 180 degrees apart. Since our molecules are really three-dimensional objects, we can represent the atoms using the space-filling model to give the most accurate representation of relative atomic size and how squished together the atoms really are. We have CPK coloring to help color code the different elements. Nitrogen is blue. That color doesn't turn out too well. And then this is space filling. And as you can see in the space filling, sometimes it's a little hard to tell what's in the back there. And so a ball and stick model shows the covalent bonds as sticks and the atoms as balls. In this wedge dash feature drawing, the opaque wedge here means it's like coming out at you, coming out of the plane of the board, and the dashed wedge means it's going behind the board. And then in the plane of the paper is the regular straight line. So let's practice drawing a wedge dash structure of acetic acid. The ball and stick model is presented here. Go ahead and pause the video and try to draw the ball and stick model in your notebook. Then identify what the geometry is around each atom and what is the ideal bond angle for each bond. Okay, let's try to sketch this out. So black represents carbon, and I see that carbon is covalently bonded to another carbon, and that looks like it's in the plane of the board, and then I see a double bond to a red atom, which represents oxygen, and a bond to another oxygen, and a bond to a hydrogen. This hydrogen looks like it's going behind the plane of the board. So I'll draw a dashed line back. And then that one looks like it's kind of coming out at me. And so that's kind of a wedge dash structure. That's another way of doing it. Let me clean up my drawing. So this carbon here has 1, 2, 3, 4 electron groups, which makes it tetrahedral. And that means that its bond angle is 109.5. This carbon has 1, 2, 3 electron groups around it, and so it's trigonal planar, which gives it a 120-degree bond angle. Structural formulas in 2 dimensions can be either Lewis-Dot structures, expanded structural formulas, condensed structural formulas, or skeletal formulas, also known as line angle structures. Lewis-Dot structures take a very long time to write, but they give the most detail. Expanded structural formulas give the second most detail, but they leave out the dots for the lone pairs. And then here in the condensed structural formula, the bonds between carbon and hydrogen are condensed. And then here, the carbons and hydrogens are implied and they're not even written. So let's look at the features of an expanded structural formula and a condensed structural formula. That way, if you're asked on an exam to draw an expanded structural formula, you know the difference between an expanded structural formula and a condensed structural formula. So expanded structural formulas are based on the Lewis-Dot structures, and so you will still draw the covalent bonds between all the atoms. So all the bonds are drawn. What's not drawn is the lone pairs. And so on oxygen, we know that this oxygen really does have an octet, and so if it has 2 covalent bonds, it must have 2 lone pairs. Just the lone pairs are not drawn. They are there, but you have to know that they're there because of everything needing to follow the octet rule. Condensed structural formulas are where these bonds between carbon and hydrogen are condensed. And so anything written after the carbon are implied to mean that they're bonded to the previous carbon. And so you kind of read across and you're like, carbon, everything bonded to that carbon. Carbon, everything bonded to that carbon. So when you do a condensed structural formula, you are allowed to bump out in order to show the bonding to another functional group or off of a branch or something. You are allowed to do that. But there's other ways of doing it as well. You can also show in parentheses what is bonded to something. If you have multiple different groups bonded, you can use parentheses. You can, this is a carboxylic acid, and this is an acceptable way of writing a carboxylic acid functional group on a molecule. And we'll be going over the acceptable ways of writing functional groups as we go along. But sometimes students are a little uneasy about the condensed structural formula at first because there's so many different possibilities of how to do it correctly, and they really just want there to be one way. But really, that's okay that there's multiple acceptable condensed structural formulas. So let's practice writing the condensed structural formulas. So we can see that this molecule here has 4 different carbons. We're going to kind of read these across from left to right and write out what's bonded to the carbon. So that first carbon has 3 hydrogens bonded to it. The second carbon has 2 hydrogens bonded to it. The third hydrogen has 2 hydrogens bonded to it. And then the last carbon has 3 hydrogens bonded to it. So you just kind of read across. If you do notice that you have a repeating unit in the middle, then you are allowed to condense it further to abbreviate it. This becomes particularly important when we talk about our fatty acids, because you don't want to keep writing out CH2, 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 CH2. There's 1, 2, 3, 4, 5 CH2s, and so you would just want to abbreviate that like that. It's much easier, much faster, saves a bunch of headache, and it's all good. So here's an example problem. I'm going to be writing the condensed structural formula for this molecule. And so this molecule is one of the molecules responsible for the smell of old books. So let's start here. This carbon has 3 hydrogens bonded to it. The next carbon has 2 hydrogens bonded to it. The third carbon has 2 more hydrogens. This carbon also has 2 more hydrogens. This carbon has 1 hydrogen, and then it has this coming off of it. So I am allowed to write up above or below, it doesn't matter, that branch that comes off of it. I could also continue that part in a straight line and then move that coming down below. You have options, and it's okay. So this has a CH2, and that's a CH3. And I could have written that here as well. Either way is okay. And so I could have also put that CH2, CH3 group in parentheses and then continued with the HOH. There's a lot of different options here for you. Here's a practice problem. Convert this into a condensed structural formula. Pause the video and unpause the video when you're ready to check your work. Okay, let's go over this. So this first carbon has 3 hydrogens bonded to it. This second carbon has 2 hydrogens. This carbon has 2 hydrogens. That's an O, and that has 2 bonded to it, and that has 1. You can abbreviate these two CH2s together, so you can write CH3, CH2, and then 2 of those, O, CH2Cl. What you can't do is move this CH2 over to condense it that way, because we have to still convey the structure of the molecule. And this carbon that has the Cl on it is not connected over here. So we still have to maintain the same bonding arrangement that we have up above. Try not to over-condense your molecule. This also speaks to how not to do a condensed structural formula. So let's take this ring structure for instance. For conveying a condensed structural formula for a ring-like structure, you would still want to label all the corners of your ring and show that they are connected in a ring-like structure. It is incorrect to break this ring open and lay it all out in one line. You're also not allowed to write CH2 and then however many are in the ring. You can't do that. You have to convey the ring shape whenever possible. The only exception to that is on Mastering Chemistry, where they'll ask you they'll only give you the text box for something, and in that case, they would accept the molecular portion of the ring molecular formula of that part of the ring, and then whatever is off of it. That's the only time, is when you're forced to do it in a freaking text box on Mastering Chemistry. Line structures are the fastest way of drawing organic molecules, but they are the least detailed. And so we will be practicing throughout the semester interconverting these two structures. It might take a week or two for you to get used to this, but it really is the best way. And it is the default for when you're using organic chemistry drawing programs, because it is so nice and so easy. Really. So it's fast because chemists are lazy. The only thing you're drawing are bonds between carbon and other carbons, and also double bonds or any bonds to heteroatoms. So all heteroatoms you actually have to write out. And yeah, that's pretty much it. So this translates, so I'm going to color code. So that blue line is that blue line. If I go up here, can I change my pen color? That'd be great. All right. And then this line here is that line. And then what color have I used? Orange. And then the double bond to the oxygen is here. And so you're just drawing the covalent bonds between carbon and other carbons, or carbons and heteroatoms. And that's it. So it goes really quickly. And then this bond here is optional. You could draw out the bond between oxygen and hydrogen, or you can just have it written as OH, and then it's implied. So for instance here, there's different line structures in this figure for the chemistry of popcorn. So let's practice converting these line structures into condensed structural formulas. I will do these two molecules as example, and you will do these ones as a practice. So let's look at these first ones. I know that in condensed structural formulas, I can draw and still convey the structure, and that's okay. What I am trying to do is label my corners so that I know how many hydrogens are on each carbon. This corner right here, I see 3 lines, and so that means that carbon must have 1 hydrogen. That's not a condensed structural formula though, because I just expanded out that hydrogen. So let me just write it in there. This carbon here already has 4 bonds, so it has 0 hydrogens left. Then this one has 2 lines coming off of it, so it must have 2 hydrogens. 2 bonds to carbon, 2 hydrogens equals in full octet. And there we go. All right, now for this molecule down here, you can see a double bond to an oxygen, and then that intersection must be a carbon down to another carbon, which has a double bond up to another carbon, single bond, double bond, single bond, and then 1, 2, 3, 4 more carbons. 1, 2, 3, 4. It was easier for me to mimic the zigzaggy shape at first, and then I can rewrite it down below without the zigzaggy shape. This carbon has 3 bonds, and so it's going to need 1 hydrogen. Here, that's going to need 1 hydrogen to make 4. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then this one's going to need 2, 2, 2 hydrogens, 2 more hydrogens, and then 3 more hydrogens. This is an aldehyde functional group, and aldehyde functional groups can be written CHO. We'll get into that when we cover the aldehyde chapter. But we can write this more in one line. I see several CH2s in a row, 1, 2, 3, 4 in a row, so I can abbreviate that. Now pause the video and try to draw the condensed structural formula for these molecules. Okay. So for our first one, we have CH3, and that goes to a C with an O bonded to it, so I can just write it like that. And then that's bonded to another C that's bonded to an O, which is bonded to a CH3. Each carbon already has 4 lines coming off of it, so there's no hydrogens on those 2 carbons. For our next molecule, I see a CH3, then I see a CH2, and I knew that there were 2 hydrogens in order to get up to 4 bonds total. Then I see a C to an O, a C to an O, and a CH3. So if you want to draw the lines in between the carbons, you can. If not, you can leave them out, and that's okay too. Here's another practice problem for you. Try to draw the line structure, the line angle structure for cyclopentanol. Pause the video and then unpause the video when you want to compare your answer. Okay, so for line structures, line angle structures, we're only going to draw these bonds between the carbons, that and that. So our line structure should look like a pentagon with an OH. And here it is.